The next section talks about solving exponential and logarithmic functions. And so let's look at the following. Let's say we have log base 10. So log of x plus 6. And this is equal to 1. So the direction says solve each logarithmic equation, express irrational solutions in exact form. So we have a log equals a number. And so we can rewrite this in exponential form. So the base of our log is 10. And so we're going to take this base 10, raise it to the other side, 1. This is equal to this x plus 6. So once we rewrite this in exponential form, it looks easy to solve, right? We can isolate x by subtracting 6 on both sides. And so subtracting 6 on both sides, we get x is equal to 10 minus 6, which is 4. When we're looking at logarithmic equations, we have to be careful because we can't take a log of a negative number. And so you just need to make sure that when you plug in your value that you've got for your answer back in for x, in this case, we want to make sure it's not log of a negative number. And it's not, because 4 plus 6 is 10. Okay, so let's look at another one. So how about if you had log base 4 of x plus 4 is equal to log base 4 of 15. Well, we can use properties of logs right here. There was a rule that said if you had a log base b of a equal to log base b of, say, capital B, then a is equal to b. So as long as our bases are the same, which they are, then we can just kind of think of it as dropping the log and saying x plus 4 would have to be 15 then. So if I subtract 4 on both sides, I would get x is equal to 11. Well, let's say you didn't see that. Let's try this a different way. So if there's more than one log in your equation, get them all to one side of the equation and rewrite it as a single log. So I could subtract log base 4 of 15 here. So this would be log base 4 of x plus 4 minus log base 4 of 15. This would now equal 0. So once we get all the logs to one side of the equation, we're going to rewrite it as a single log. And so the minus in between tells me I'm going to rewrite it as one log with division. So this is log base 4. My numerator is x plus 4, and my denominator is 15. Equals 0. Once you get it as a single log equals a number, we can rewrite this in exponential form. So exponential form says my base of my log is the base of my exponent. So I have 4 raised to the other side, which is 0, is equal to what we're taking the log of, which is x plus 4 over 15. Well, 4 to the 0 is 1. We can multiply both sides by 15 to clear our fraction. So we get 15 equals x plus 4. Subtract 4, we get x is 11. Plugging in 11 into our original equation gives us a log of a positive number, we're okay. So it was doable without this one property of logs, but knowing this property of logs makes it a lot easier. So let's look at another one. In this case, we have log of 2x, and then minus log of parentheses x minus 3 and your parentheses. This is equal to 1. So here's a case where we can't just get it a log equal a log because that 1 is in there. And so here's a case where we are going to rewrite this as a single logarithm. We have minus in between. And so we have log of our numerator, which is 2x, all over our denominator, which is x minus 3. This is equal to 1. So now we have a single log equals a number, so we can rewrite this in exponential form. So our base of this log, since it's not shown, is 10. So we have 10 raised to the first power equals 2x, all times x minus 3. So let's clear the fraction. We can multiply both sides by our denominator of x minus 3. Distributing our 10 to x minus 3, we get 10x minus 30 equals, x minus 3 just cancel there. That was the whole purpose of that, equals 2x. Well, let's get variables to one side, constants on the other. So let's subtract 10x on both sides. So 2x minus 10x gives me negative 8x equals negative 30. Divide both sides by negative 8. We get x equals negative 30 over negative 8. Both of those have a 2 in common, and they're both negative, so it's positive. So we have 15 fourths. We need to make sure that when we plug this back in, we don't get a log of a negative number. And so if we plug it back in for x here, 2 times 15 fourths, that's positive, and 15 fourths minus 3. Well, I notice 15 fourths is a little bit bigger than 3. And so some number bigger than 3 minus 3 is positive. So we're okay. And we have our solution. Let's say you had log base 2 of x plus 3 is equal to 1 minus log base 2 of x minus 1. Okay, so to solve this, we want to get all the logs to one side of our equation. So we get log base 2 of x plus 3 plus log base 2 of x minus 1 is equal to 1. We can now rewrite this as a single logarithm. Addition in between our logs tells us multiplication. So this is log base 2 of x plus 3 all times x minus 1. This is equal to 1. We can distribute now or we can distribute later. Rewriting this in exponential form, our base of our log is 2. That's the base of our exponent. 2 raised to the first power is equal to, let's distribute this out while we're working on it. So x times x, x squared. We're going to have a negative x plus a 3x. So that's a plus a 2x. And 3 times negative 1, that's minus 3. So notice that we have a quadratic. We can get everything to one side of the equation and solve. So let's subtract 2 on both sides. We get x squared plus 2x minus 5 equals 0. So unfortunately, this doesn't factor. So let's use our quadratic formula. So we have x is equal to negative b, so negative 2 plus or minus the square root of negative b squared, which is 4, not negative b, doesn't matter because it's squared, but b squared, which is 4, minus 4 times a, which is 1, times c, which is negative 5. all over 2a, so 2. So square root of 4, this is really plus 20, so this is the square root of 4 plus 20, which is 24, all over 2. So we can pull out square root of 24 is 4 times 6. So we can pull out the square root of 4 and rewrite it as 2. So this is x equals -2 plus or minus 2 root 6 all over 2. I notice 2 goes into both -2, goes in a negative 1 time, plus or minus 2 goes into 2 root 6 times. We need to be careful here because we can't have a log of a negative number. I notice right now, because this is two separate solutions, x equals -1 minus root 6. When I plug this into this log, those are all negative numbers. I can't have a log of a negative, so this one doesn't work. If I look at x equals -1 plus root 6, let's figure out what that is. Well, root 6, that's between square root of 4 and square root of 9. So that is 2 point something. 2 point something minus a 1 is 1 point something. So I'm okay when I go in here and plug in my 1 point something minus 1. That's going to give me a positive number. And so I would be okay with that. So our solution is just this one. Okay, so solving log equations, get logs all to one side, rewrite it as a single log, get your constant on the other side, rewrite it in exponential form, and then solve depending on what kind of equation you have once you rewrite it. So our next equation is log base x, that whole log base x is squared, minus 3 log base 3 of x equals 10. That square is different. If that's saying log base 3 of x all times log base 3 of x. I can't bring that 2 down. And so I noticed that I can manipulate this to look like a quadratic equation. So let u equal this log base 3 of x. So if we do that, right here, we would have u squared minus 3. We have that log base 3 of x again, so times u. I'm going to subtract 10 on both sides to get this equal to 0, so minus 10 equals 0. So now I have a quadratic. It's a quadratic that I know how to factor. So there are two numbers that multiply to -10 and add to -3. So we have u minus 5 all times u plus 2. So u is either equal to 5 or u is equal to -2. We want to know what x is, not what u is. And so let's go and rewrite this as two separate equations. So we have u, which is log base 3 of x is equal to this 5. And we have this log base 3 of x is equal to this -2. So let's solve each one of those logs separately. Let's rewrite it in exponential form. So this is saying 3 raised to the 5th power is x. So 3 times 3 is 9, times 3 is 27. 27 times 3 is 81, and 81 times 3 is 243. Okay, so let's look at the second log base 3 of x equals -2. Let's rewrite it in exponential form. So we have 3 raised to the -2 power equals x. We can rewrite that negative exponent. We can bring that down to the denominator and make it positive. So we have 1 over 3 squared, which is x equals 1 over 9. We need to make sure we're not having a log of a negative number. Back in our original equation, those are both positive numbers, and when I plug them in for x, I have a log of a positive, so I'm okay. There's nothing I have to exclude in this one. So I have two solutions. X equals 243 and x equals 1/9. So we looked at solving exponential equations before, but these exponential equations we solved before, we can manipulate the bases to be the same. For instance, if we had 5 raised to the negative x power is equal to 25. We could use that rule. If we can get the bases to be the same, b to the y equals b to the x, then that y equals x. B can't be 0, B can't be 1. Actually, B can't be less than 0 either. So less than or equal to 0. Our base has to be positive. So B has to be greater than 0 and B can't be 1. Okay, so we can manipulate 25 to be base 5. So this is 5 raised to the negative x is equal to 5 squared. Using this rule, now we have negative x is equal to 2, so x has to be negative 2. Okay, so it's not always the case that we can manipulate those bases to be the same. And so if we cannot manipulate those bases to be the same, we're going to use our rules of logs. So we're going to use the fact if we have two things equal to each other, then we can take the log of both sides and they're still going to be equal to each other, as long as what we're taking the log of is positive. So when you use that fact, we're also going to use the fact that if we have a log base something b of a raised to some power x, we can bring that power down front. So x times log base b of a. So you're going to use those rules if we can't manipulate our bases to be the same to help us solve an exponential equation. So let's say that we have 3 raised to the x is equal to 14. So 14 cannot be manipulated to be base 3. And so we want to use properties of logs to help us solve this. And so we can take the log of both sides of our equation, or the natural log of both sides of our equation. It doesn't matter which one. You're going to use log base 10 normally, or log base e. I usually use natural log. So we have the natural log of 3 to the x equals the natural log of 14. Rules of logs, though, says that I can bring my exponent down front. So we get x times the natural log of 3 equals the natural log of 14. So we can get x by itself right now by dividing both sides by the natural log of 3. So we have the natural log of 14 divided by the natural log of 3. So if they want it in exact form, this is how you're going to leave it. We could, if they wanted it simplified, we could plug in the calculator if they wanted decimal form. So natural log of 14 divided by the natural log of 3. This gives us approximately 2.4. And we can look at that, right? And we could determine that seems reasonable. If I squared 3, that's 9. 9 is less than 14. But if I cube 3, 3 cubed is 27. And so that's bigger than this 14. So we know that our answer has to be between 2 and 3. So what if you have 4/3? This is all raised to the 1 minus x power equals 5 all raised to the x power. So here's another example where we're not able to manipulate those bases to be the same. So we're going to use our properties of the logs to help us rewrite this. And so let's take the natural log of both sides of our equation. So the natural log of 4/3 all raised to the 1 minus x equals the natural log of 5 all raised to the x. So we're going to use rules of exponents and logs that we can bring these down. Be careful though, because if there's more than one term in that new exponent, then we need parentheses around that whole thing. So there's parentheses 1 minus x, then that natural log of 4/3 is equal to, bringing the x down, x times the natural log of 5. We really want all the terms with x in it on one side of the equation, all terms without x on the other side. Let's distribute this natural log of 4/3 inside this parentheses. So 1 times the natural log of 4/3 is natural log of 4/3 minus, we have x natural log of 4/3 is equal to x natural log of 5. So getting all the terms with x in it to one side, so let's add that x natural log of 4/3 to both sides. So we have natural log of 4/3 equals this x times the natural log of 5 plus x times that natural log of 4/3. So you have the natural log of 4/3 equals, we can factor out an x there. So let's pull out an x from both of those terms. We have the natural log of 5 plus the natural log of 4/3. We're almost there. We can divide both sides by that bracket, and then we have x by itself. So we get x is equal to that natural log of 4/3 all divided by the natural log of 5 plus the natural log of 4/3. And technically, that natural log of 5 plus natural log of 4/3, I can rewrite that as a single log with multiplication if I wanted to. So this could be x is the natural log of 4/3 all over the natural log. Well, 5 times 4/3, this would be 20/3. And then I'm seeing I could definitely rewrite it, getting rid of the fraction and rewriting that as a minus sign, but I don't know. This is just fine. We cannot cancel those natural logs. Okay, so that would be the exact form. So I believe some of the homework is going to ask you for the exact form and then to approximate it. So see one other one in here that's similar to that one that last problem we did with the logarithms, where we can rewrite things so that it is an exponential, so that it is in quadratic form. So let's say you had 9 raised to the x power minus 3 raised to the x plus 1 power plus 1. Equals 0. And we want to solve this. Okay, so I noticed that 9 is the same thing as 3 squared. And so we can rewrite this a little bit. Let's use rules of exponentials. So we can rewrite this as 3 squared raised to the x minus The problem with this is that I have this 3 raised to the x plus 1 power, but we can use rules of exponents. This is the same thing as 3 to the x times 3 to the first. And then this plus 1 equals 0. So let's write it a little differently. So this is the same power to power is multiplying. So this is the same thing as 3 raised to the 2x minus 3x plus 1 equals 0. Okay, so same idea. I just want to rewrite it a little more. I can rewrite this. This is the same thing as 3x, and then I'm squaring it, minus, oops, and I dropped my 3 here. We didn't want to drop this little 3. So let's put that out front here. 3 all raised to the 3x plus 1 equals 0. So notice here that we can let u equal 3 to the x. 3 raised to the x power. So if we go do that, we would have this u, then it's squared, minus this 3, then this u plus 1 is equal to 0. Okay, so unfortunately, again, this one is not factorable, so we need to use the quadratic formula. So if we let u equal negative b, so positive 3 plus or minus the square root of b squared, which is 9, minus 4 times 1 times 1, all over 2. So we have 3 plus or minus the square root of 5 all over 2. Okay, so we have 2 separate answers. We have 3 plus root 5 all over 2. That's our u value. We know that this is equal to 3 raised to the x power. We also have 3 minus root 5 all over 2. And this is equal to 3 to the x power. So now we can take logs of both sides of the equation, bring our exponent down, and solve. So take the log base 10 or log base e, natural log, to both sides. So if I take the log of both sides, I got the log of 3 plus root 5 all over 2 equals log of 3 to the x. Let's bring our exponent down. So the same thing as, I'm going to write this on the right, our left-hand side, x log base 3, or log base 10 of 3, sorry, equals log of 3 plus root 5 all over 2. So we can divide both sides by that log of 3. So we get x equals log of 3 plus root 5 all over 2 divided by a log of 3. So there's one solution. The other solution, same idea. We could take the log of both sides. So we have the log of 3 minus root 5 all over 2 equals the log of 3 raised to the x. Bring our exponent down. So log of 3 minus root 5 all over 2 equals x times log of 3 Divide both sides by log of 3, and we have our second answer. So x equals log of 3 minus root 5 all over 2 divided by log of 3. Okay. So our answers aren't always looking very nice now, but we solved it. Okay, so like I had mentioned before, exponential equations and logarithmic equations a lot of times represent real life application. And so a depreciation of a car could be looked at as an exponential decay. So depreciation, the value V of the Honda Civic LX that is T years old can be modeled by the following equation. And so we're given that V of T is equal to 19,705. And this is all times our base 848. And then that is all raised to the T power. So part A wants to know, according to the model, when will the car be worth $14,000? So we're not trying to figure out when is the value worth $14,000. And so that's what V of T is. So we're going to have 14,000 is equal to this 19,705 of this 0.848 raised to the T power. Before we can take the log of both sides of the equation, we want to isolate this exponential piece. So let's first divide by the coefficient in front, 19,705 on both sides of our equation. And so doing so, we have this 19,000, we don't. We have, I'm going to put the exponential piece on the side. So we have 0.848 raised to the T power is equal to 14,000 divided by 19,705. So let's take the log of both sides of the equation. So ln of both sides. So we can bring down our exponent. So now taking the natural log of both sides, we can bring down the exponent of x, or t, in front of our natural log. And so we get t, natural log of this 0.848 equals the natural log of the 14,000 divided by 19,705. So divide both sides by that natural log. And so we get t is equal to the natural log of this 14,000 over 19,705 divided by this natural log of 0.848. So plugging it in. Making sure I'm trying not to type anything in wrong. And so this gives me approximately 2.1 years. Let's say we wanted to know what the original value of the car was. So the original value of the car, that would be when t is 0. If you looked at v of 0, that would give us that 19,705. Anything raised to the 0 power is 1. So our car depreciated $5,705 to get down to $14,000 in 2.1 years. And then it wanted to know, according to the model, when will the car be worth $10,000? And so it would be the same sort of setup, except instead of 14,000, we're going to write 10,000. So 10,000 equals this 19,705, 0.848 raised to the t. So we can divide both sides by that 19,705. We can take the natural log of both sides of the equation, so we can bring the t down front. I'm just going to write the t in front right now because we're running out of time. So you have t times the natural log of the 0.848 equals the natural log of the 10,000 divided by 19,705. Divide both sides by that natural log. So we get t is equal to the natural log of the 10,000 divided by 19,705 divided by that whole thing. Natural log is 0.848. So plugging it in. So natural log of 10,000 divided by 19,705, then divided by natural log of 0.848. This gives me approximately 4.1 years. Okay, so that was section, I believe, 5.6 in our textbook. And I might be totally off now. Sorry, this was actually 6.6 in our textbook.